Okay, electric current. There's my T. So let's just go ahead and define the electric current. The electric current is defined as the rate of change of charge. It's the charge flow rate. So imagine I have some metal, or it could be anything, and I have positive charges in there, they're moving. And if I take the time of some interval delta t and a delta q charge flow past that point in that amount of time, then delta q divided by delta t is the current. So if q is measured in coulombs and t is in seconds, then that's a coulomb per second, which we call an ampere. You can call it an amp. Okay, so 1 amp of current is actually pretty high. Okay, so let's think about what's actually going on here, though. Some really important things. First of all, imagine that I have a positive charge Q, and I apply an electric field E. Then what's the motion of this charge going to be like? Well, there's going to be a force on it this way, and it has mass, so that means it's going to accelerate. So if I plotted the position as a function of time, it would look like, well, let's look at the velocity as a function of time. The velocity as a function of time, it would just keep speeding up. Constant force, keep speeding up forever. Now let's say I take this. This is a container of salt water, and so it has both positive ions in it and negative ions in it, and they're moving around. Now let's say I put some bars in here and I apply, again, a constant electric field, E. So now in this case, these positive charges are going to experience a force and they're going to accelerate. But they can't keep accelerating forever. They're actually going to have a collision with the other molecules in the water because there's stuff there. So if I plot V versus T, it's going to go like this. It's going to speed up and then it's going to collide and stop. But the electric field's still there, so it's going to speed up and it's going to collide and stop. Maybe this time it didn't go as far, and then it's going to speed up and keep speeding up and stopping. So although it's accelerating, we can think of some average velocity that it has, v average. And we call this the drift velocity. So if I apply an electric field, a constant electric field, I get a average constant velocity. If I increase the value of the electric field, I get a higher drift velocity. Because if I accelerate these faster, everything's going to be higher, and I'll have a higher average. So it turns out that we have the following relationship. The drift velocity, I'll call it Vd, is U times E. These are all magnitudes. So here, U is called the charge mobility. It tells you how easily charges are able to move in that material before they have a collision with something like that. But this is the important thing. It says, why do we have moving charge? Because there's an electric field. Now, once I have moving charges, I'm going to have a current. And let's show what that current would be. So suppose I have a metal wire like this. And I have, in this case, metals have positive and negative charges in them. But you can't really move the positive charges. If this is iron, the positives are in the atomic core of that iron. It's not really just going to move around. The whole atom's not going to move around. However, the outer electrons are able to move from one core to the next, so the electrons are able to move. If I apply an electric field, let's say this way, then there's going to be a force on these charges pushing it that way. They'll speed up and still have collisions, and they'll have an average drift velocity. So I will get a current going this way. And it turns out that the current is equal to Q in a V drift velocity. So this says that the flow rate of charge depends on the magnitude of the charge. In this case, if they're electrons, E is equal to Q is 1.6 times 10 to the negative 19th coulombs. That's the charge of an electron. But it doesn't have to be. It could be an ion. It could be anything. N is the charge carrier density. In number per cubic meter. So this tells you how many free electrons you have per cubic meter. The more you have, the higher the current. A is the cross-sectional area of your wire. Because if I have a thicker wire, then even with the same electric field, I'm going to get more charges flowing. And then V is the drift velocity, which depends on the electric field and the mobility. So A, cross-sectional area. Okay, so I think that's good enough for now to think about electric current. We are a lot of times just going to deal with electric current on its own and not worry about a whole bunch of other things. But it's important to realize what's really going on. Oh, one more thing. We have I is the conventional current. This is the possible flow of positive charge. So even in this case, if I have the negative charges moving, actually, this is V, not I. I would actually be this way. The conventional current would be that way. The conventional current shows the direction of positive charge flow. So even if I have negative charges moving this way, it looks the same as if it was positive charges moving that way. In most cases, there is a way we can tell those apart. But the conventional current is the direction of positive flow charge if its positive charge is flowing. So it would be the negative velocity if it's an electron flow. Okay, but a lot of times you can't tell the difference, so we just call it conventional current, flow of positive charge. Okay, we'll use electric current in some more stuff coming up soon.